taking limits of polynomials, rational functions, and other sorts of functions, we still have a little bit more algebra of limits to talk about. We've seen basic limits, which gave us 3 limits that are very basic and essential to doing what we're going to be doing. Here now are limits of sums, differences, products, quotients, and roots of functions. So we will start by saying that the rules of algebra for limits are what we are about to discuss. Now, to do that, I'm going to say let's let A be any real number. So every time you see an A, it'll be just a real number. And I'm going to want to talk about limits, so we will suppose that we have 2 limits that exist. The limit of the function f of x as x approaches a is some number L sub 1. So that is saying that it exists, it equals a real number. And we'll need another one to talk about. The limit of a second function g of x as x approaches a, which is L sub 2. Then, with those functions and that real number in mind, we can construct a laundry list of the various properties that limits have with relation to functions and differences and sums, products and quotients and roots. So let's start with the simplest one, the first one. Let's take the limit as x approaches a of the sum f of x plus g of x of 2 functions. Now we know how to take the limits of them individually. The question here is, if you add them, how does the limit function? Well, it turns out to work exactly the way you would hope it would work. This is the limit of f of x as x approaches a plus the limit of g of x as x approaches a. Now, since we call the limit of f of x L1 and the limit of g of x L2, we can write that as L1 plus L2. Now, later in this course, as we start talking about other aspects of calculus, you'll find out that symbols that we use there do not always work over sums as easily as limits do. There may be other things that happen. The same thing with differences, products, and quotients. So keep in mind, although this looks very easy now, and it is, later on there will be other complications to consider. Well, we did sums. What is the story with a difference? Well, luckily, it is exactly the same. If you take the limit as x approaches a of f of x minus g of x, that is exactly the same thing as taking the limit of the first function f of x and subtracting the limit of the second function g of x, both as x approaches a, and you then get L1 minus L2. So those were the easy cases. Let's now look at a couple of more interesting cases. The next one in line, of course, is the product. So let's talk about the product and some of its implications. If you want to take the limit of f of x times g of x, and I will try and emphasize the multiplication here with a dot. If you want the limit of f of x times g of x, luckily, again, this gives you exactly what you would expect. The limit of f of x as x approaches a times the limit of g of x as x approaches a. And throughout all of this, you surely have noticed that the limits have to be the same here because they were both the same here. They're both as x approaches a. Now, rather than just leave the product here and move on to the quotient, let us take a moment and look at some implications that follow from this product rule. The implications are f of x and g of x could be the same function. F of x, g of x could gather together with other functions. There could be 2 functions here, there could be 3, there could be 4, there could be 5, and more. Also, one of these functions might be the constant function. All of these things allow us to talk about certain applications of this rule for taking the limit of a product of functions. Suppose we take the limit, with the last one I mentioned, of k times f of x. So I have a constant function times an unknown function. Well, the rule says take the limit of the first one times the limit of the second one. But k is a constant, and as you know, the limit of a constant is just the constant itself. So this becomes k times the limit of f of x as x approaches a. And what we've learned from this is that the constant simply came out front of the limit. That's the way to remember this. The rule is the product rule up here, correct. And the limit of the first one happens to be k, the constant function. But if you want to remember this in practice, if you're taking the limit of a constant times a function, the constant simply comes out or passes through the limit. That's the easiest way to remember that. Here's another example that flows from that product rule above. Suppose I take a limit of the function f of x taken to the fourth power. This is just f of x times f of x times f of x times f of x. That's the product. This rule says it breaks apart into the limit of each one of them multiplied by all the others. Well, they're all the same. So this is the same thing as the limit of f of x as x approaches a, all taken to the power 4, because the limit of each one of these is the same thing. So here's another way that the power can pass through the limit sign and come outside if you have a single function taken to a power. Finally, if we take an even more special case of that, if we take the function to be x to the fourth, then this reads the limit of x to the fourth becomes the limit as x approaches a of x to the fourth power. And we can go further here because this is one of the basic limits. And the limit of x as x approaches a is a. So this is a to the fourth power. Now the one above, just for the record, the limit of f of x, you may recall we call that the number L1. So this is the number L1 to the fourth power. So here are three cases that follow immediately from the limit of the product of two functions is the product of the limits. And these were written down not because they are new, but because they are very helpful and useful in practice. Now let's move on to the quotient rule for limits. So the limit as x approaches a of the quotient f of x over g of x. Now by now you should be able to guess what you think this ought to be. This ought to be the limit as x approaches a of f of x on the top divided by the limit as x approaches a of g of x. And if we use the letters that we used to represent these two limits before, that would be L1 over L2. But now we have to pay attention. Whenever we have a fraction anywhere in any mathematical situation, we have to be aware that the denominator, the bottom, cannot be 0 because division by 0 is undefined. So this will be true provided that L2 is not 0. And L2 is the limit of the g function. As long as that's not 0, the quotient rule here works. If the limit of the bottom function is 0, then this rule no longer functions. The last rule that we mentioned in the title of this section was the rule that said what happens when you take the nth root of a function and you ask yourself what is the limit as x approaches a. Well, as it turns out from everything else that you've seen today, this ought to be, if all is right with the world, the nth root of the limit of f of x. And that would be written as the nth root of L1. Now, that is correct. That's exactly what this is. We're leaving the proof out of this, but I think you can see from examples that this is true. However, yet again, we have to pay attention. If n is an even number, if we are taking an even root like a square root or a fourth root or a sixth root, and L1 happened to be a negative number, this number would not be undefined but would be a complex number. And since we're doing calculus of real variables on real numbers, we don't want this to be allowed to be a complex number. So we will say here that this is true provided when n is even, then L1 is greater than or possibly equal to 0, because any root of 0 is going to be 0. Now let me mention one other little note here. You may notice that when I write my square root symbols, I put a tail on the end. That's a very wise habit to develop because it gives you a chance to mark where what is underneath this square root or whatever the nth root is actually ends. When you're writing things out, that becomes very useful. Not so useful when you're printing things in a textbook, but when you're writing it by hand, this little tail can be very useful. Now, all of the limits we did here for the quotient, the root, and previously for the sum and the difference, all of them hold not only if x is approaching a, but also if x approaches a from the left or a from the right. All of these rules will hold with the same provisos in these two cases. So we actually have seen a completely general set of arguments, and we now know how to take functions that are made up of other functions and break them apart when we're interested in taking the limit. Now let's go ahead and do that by looking at some specific cases, such as polynomial. Now we want to talk about the algebra of limits. And we're going to break it into two parts. The first part, as you see, is where x is approaching a real number. Now it may approach a from the right, the left, or both sides, but it will be a real number. We'll save the infinity case for later. Now the algebra of limits section will actually teach us how to calculate limits. We have seen an intuitive idea of what limits are about, and now we want to actually get in there and do the technical business of calculating. So, basic limits are where we'll start. So, the very first basic limit is almost common sense, but I hope you'll bear with me as we work our way up to the more difficult cases. Suppose we consider the constant function. Now we say the constant function, but really there are an infinite number of constant functions depending on what constant you use. The constant function has the form f of x equals k. Now k is a constant. Now that's a very dull function to look at. If we look at its graph, for example, and if I suppose for the sake of my drawing that k is a positive number, let's just mark k up here, then what's the graph of this function? It's simply a horizontal line, y equals k. F of x, of course, is y, so f of x equals k is y equals k. It's just a horizontal line at the height k. Not a very interesting function. And it's very easy to find any limit of this function. For example, if we take an arbitrary real number a on the real number line, and we ask ourselves, as the x's come in and approach a, what happens to the height of the function? Then we have a very easy answer. The height of the function is constant. It never changes. So that means if we take the limit of the constant function k as x approaches a, then we should expect that we get k. Constants are constant. They don't change. It doesn't matter what x is doing. So the way we say that is the limit of a constant is that constant. And if you want a simple example, you might say, what is the limit of 2 as x approaches 3? Now if you understand the concept, you have no difficulty writing this down. If you don't understand the concept, I have seen students who try to multiply 2 and 3 or add 2 and 3 or do some other operation. In fact, this is the limit of the constant function 2 as x approaches 3, but we don't care what x approaches because this is constant. And so it's just equal to 2. So there's the constant function, the first of the basic limits. The limit of a constant is that constant. Let us go on and look at another very simple function, which is a step above, the identity function. Okay? This is the function f of x equals x. In other words, it's the function that doesn't do anything to x. It simply repeats it, or echoes it, if you like. This also has a very easy graph. It's simply the 45-degree line. Because if f of x equals x, that can be interpreted as y equals x, and that's a line that everyone knows. And if we are interested now in the limit as x approaches a, then it would seem to be approaching a height of this point. And if we come over here, what is that height? Well, the y and the x values are the same, so this height is the height a. That is the reason why we write down in symbols the limit as x approaches a of x equals Well, if you just listen to what I said and what you say as you're working this problem, what is the limit of x as x approaches a? What does x approach as x approaches a? Well, of course, it approaches a. We're saying the same thing twice, it seems. So, for example, you might try the limit of x as x approaches 3. Well, that's 3. So, the identity function here and the constant function here are both functions for whom the limit is very easy to take. But we have to start somewhere, so we've started at the bottom, and we have some basic limits now to work with. There's one other basic limit we'll go ahead and say something about now. This is what might be called the reciprocal function. Or if you don't like the word reciprocal, you could say it's the flip-over function. And you know what? This is the function we've been talking about at length. F of x is 1 over x. That's the function that simply finds the reciprocal of the number x, which is 1 over x. Now, unlike the other two cases we just looked at, instead of looking for an arbitrary a value, we will only consider in this case the value of a equals 0. Because that's where things are most interesting. As you know, the graph of this function looks something like this. Whoops. I drew that line so it actually ran into the axis, but you know that it doesn't. So here we are asking the question, what happens as x approaches 0 from either side? Well, you also know the values of this because we've looked at it before, but now we can read it carefully. The limit of 1 over x as x approaches 0 from the left. As x is approaching 0 from the left, what is the function doing? The function seems to be heading toward negative infinity. And that's exactly what we write here. So the limit of 1 over x as x approaches 0 from the left is negative infinity. But notice, of course, that if we approach x as x approaches 0 from the right, we get infinity, because as x approaches 0 from the right, the function is growing without bound. So we have here two more very basic limits. The limit of the reciprocal or flip-over function as x approaches 0 from the right or from the left. And we get two different sorts of infinities depending on which direction you go. Now this is something that happens very often, so it is among the basic limits so that we'll have something to talk about later. Now why were these three limits called basic limits, apart from the fact that they seem to be very simple? Well, why basic? They are used in some very familiar functions that we're going to be looking at. Polynomial functions and rational functions. And yes, from time to time I will abbreviate words like function in some fashion, as I have done here, so don't let that disturb you. We are going to examine now polynomial functions first and then rational functions. But even before that, we need a little bit more of the algebra of limits, and that's coming up next. Now it's time to take the limits of some very familiar functions, the polynomials. So that's what we'll do next, limits of polynomial functions. And we'll start by doing an example from which we can illustrate the general principle. So we want to find here the limit as x approaches, say, 5 of the following polynomial, x squared minus 4x plus 3. This will allow us to talk about all the issues involved here. So, solution, we just have one solution. By the rules of algebra for limits, which we talked about previously, by the rules of algebra for limits, we can break down this function, there's that abbreviation of function, into simpler parts. And once they're simple, we hope we'll be able to take the actual limit using our basic limits or using one of the properties we've learned. So let us write out again what we're going to do. The limit as x approaches 5 of, and I'll spread this out a little bit, x squared minus 4x plus 3. Now, the first thing you notice here is that you have a difference and a sum. We'll use those rules to break this up into 3 terms. So this will become the limit of x squared as x approaches 5 minus, and see, here's where the difference comes in, and this is the difference rule that we learned. The limit of a difference is the difference of the limits. So this is now the limit as x approaches 5 of 4x. Then we have a sum, and so we will add now. This is where the sum rule will come in, and we'll have the limit of 3 as x approaches 5. Now, in this first limit we see we have x squared. That is a product, so we'll have to think about the product property. Here we have another product. We'll use the product property again. And 3 is a basic limit, so we can take that limit immediately. So now we will have the limit of x quantity squared as x goes to 5, because that's a product, and that's how the product rule we learned works. This is also a product. It's a product of a constant times a variable function, x. So we learned already that we can pull the constant out front. So this becomes 4 times the limit of x as x approaches 5, plus, and the limit of 3, being a constant function, is just 3. Now we have reduced both of these. So if we want to put a note here, we can say this is from a basic limit. Both of these now are basic limits. That's the limit of x, and this is also the limit of x. So this becomes, as x approaches 5, the limit of x is 5. That's 5 squared, minus 4 times the limit of x as approaches 5 is 5, plus 3. And so that's 25 minus 20 plus 3 is going to give you 8. There is the value of the limit of this original polynomial as x approaches 5. So this limit is a real number, and we broke this down into pieces in order to show you how all the various rules we talked about were being used. Now when you do this in practice, you will not be breaking this down so many steps. You will probably jump very quickly to the end. And in fact, the theorem coming up will help us see that that is the case. So let's look at a general theorem about polynomials. Theorem. For any polynomial, and actually we should say for any polynomial function, that's more correct. So for any polynomial function, and you can write it out, say, call it the function p of x, p for polynomial, has the following form: c0 plus c1x plus dot 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 up to cn x to the n, where the c0, c1, and cn, these are all constants, multiplied by powers of x, here multiplied by no x at all, or the x to the power 0 if you like, then the first power of x, all the way up to whatever the highest degree power is in this polynomial. For any such polynomial function and any real number, say a, we have the following. If you take the limit of the polynomial as x approaches a, using, if you wanted to prove this, you could use all the rules that we've seen. Using the rules, it turns out to be this. Now see how this works out. c0 plus c1a plus all the way up to cn times a to the n. In other words, that's the polynomial evaluated at a. This is a very, very useful fact, and one that's worth mentioning carefully. Notice, for polynomials, or polynomial functions, this limit is the same thing as substitution. Substitution what? Of a for x. Now that's an important point to make. We have been learning this new concept called the limit. We have seen many cases where the limit is absolutely necessary. It is about approach and destination, remember, and the limit doesn't care much about the destination, it's all about the approach. And we saw examples earlier where there were cases where the limit didn't exist or had different properties from what you would think of as simply, in this case, substitution. But in the case of a polynomial and many simple functions, if we simply take this a value and substitute it here for x, we get the value of the limit, p of a in this case. That works for polynomials. It will also work for rational functions as we start looking at them. It works for some other functions too. But the warning here is, do not think that whenever you're taking a limit, simply by taking a and putting it in for x, that you will get the value of the limit. It all depends on what the function is. In this case, we're lucky. It's very easy. In most cases, it's not. Keep that in mind. Now we'll look at limits of rational functions. We looked previously at polynomials, but now we're going to look at the limits of rational functions and the apparent appearance of 0 over 0, which is an undefined expression. What could that mean? Let's see what happens. So, to begin, let's recall what a rational function is. Just to be absolutely clear, a rational function is equal to a polynomial over another polynomial. So if you write it out using functional notation, if I call the rational function f of x, I can think of it as a polynomial p of x over another polynomial q of x. And once I've got it written that way, I realize a couple of things. What I learned about polynomials probably has some bearing on rational functions and limits. Also, because a rational function does have a division, I need to be aware of division by 0. So I must avoid division by 0. And that's something I need to keep in mind. There will be 3 cases to consider here. And you'll see what they are in a moment, but what they revolve around is whether or not q of x is 0. If this is 0 and the top is not 0, we have one result. If this is 0 and the top is 0, we have a second result. There is a third result where neither is 0, and that's the easiest one. In fact, the one we'll start out with. Let's recall what we know about polynomials so we can apply it here. Recall, for polynomials, letting x go to a is exactly the same thing as, substituting a for x. So taking a limit with polynomials is very, very easy. With that in mind, we might expect the following. We might expect that if I take the limit as x approaches a of a rational function of p of x over a q of x, where the p of x and the q of x are both polynomials, I would expect to get p of a because the limit of p of x as x approaches a is p of a, and the limit of q of x as x approaches a is q of a. So this is what I would expect, because substitution is what's supposed to happen with polynomials. Well, as we already have noted, the danger here is in the division by 0. So we have to look at these cases separately. Let us look at case 1 first. This is where q of a is not equal to 0. In that case, the limit is exactly what you'd expect. It is p of a over q of a. If q of a is not 0, there is no division by 0 difficulty, and so there's no worries. If p of a turns out to be 0, then the fraction is 0. If p of a is not 0, then the fraction is not 0. In either case, it's a real number, and we have no problems. We'll go ahead and illustrate each one of these cases with examples. So for this first case, let's take an example. This will also give us a chance to work out some problems using limits. Let's take the limit as x approaches 2 of a simple rational function 5x cubed plus 4 over x minus 3. Now, remember, the top is p of x, the bottom is q of x in our former notation, and here the letter a is 2. That is the letter that x is approaching. Now, how does one actually compute this? Well, this is a limit of a quotient, and provided the denominator does not go to 0, and of course as x goes to 2, it doesn't look like this is going to go to 0. We'll find out in a moment. The limit as x approaches 2 of 5x cubed plus 4. We take the limit of the top over the limit of the bottom. Limit as x approaches 2 of x minus 3. These are polynomials, and we know that for polynomials, limits like this are simply substitution, so we can substitute. So this is 5 times 2 cubed plus 4 on the top, and on the bottom we have 2 minus 3. If you simplify that, you get minus 44, and that turns out to be the limit. What I want to point out here is that the top here is p of a, the bottom here is q of a, where the a is 2 in this case, and notice that the q of a is not 0. So this is an example of the case 1, where q of a, the denominator, does not go to 0. And so there are no difficulties. You end up with a real number. Now let's address the condition of case 2, where things get more interesting. Case 2. Suppose that q of a is equal to 0. So now we have division by 0 as a problem. And let's take also the condition that p of a is not 0. So only the denominator, only the bottom is 0. In this case, what happens to the limit? Well, the limit does not exist. You have division by 0 after all. Right? Now, what kind of non-existence do we have here? Well, it turns out that you can either get non-existence, that is in the form of infinity, where the expression that we're going to look at grows without bound. It could be negative infinity, where it grows without bound in the negative direction or grows smaller. Or it could be that on either side of the number that we are approaching, the a value, it goes to two different kinds of infinity, one positive and one negative. We'll see examples of those. And these all fall under a sort of list of classic examples, so I'll call them that. When I mention something as classic, I don't mention it just because it's old and authoritative. I mention it because it's one of those examples you really want to remember for the rest of calculus. It is illustrating something that is important and will be repeated. So, classic examples, I'll give you 3 of them. Let's look at the limit as x approaches a from the left of the function 1 over x minus a. So here p of x is simply the constant function 1. So nothing I do with the limit will affect p of x. And in this case, q of x is the function x minus a, of course. What does the graph of this look like? Well, when x is equal to a here, we have division by 0. So that is going to give us a function which has an asymptote of some kind at a and might look like this. In this case, that's exactly what it looks like, wherever the a value happens to turn up. This limit turns out to be minus infinity because as I come from the left, that would be this direction. The function is clearly going down to minus infinity. While, if I come the other direction, I get the limit of 1 over x minus a as x approaches a from above turns out to be infinity for this same sort of reasoning. If we come from the right, the function is growing without bound. So that's the first of these classic examples where the q of a, the denominator is 0, and the p of a is not 0. This is 1 over x minus a, and we have different limits on different sides. The second example is this one. Suppose we take the limit as x approaches a, and notice now I have not put right or left. It's a two-sided limit. And we take the function 1 over x minus a quantity squared. So in this function, the p again is the 1 on the top, so it's a constant, unaffected by the limit. The bottom now, q, is this function x minus a quantity squared. If you look at the graph now, which is very similar to the previous one, if this is a, in this case, because everything's squared, the function is always positive. We have a picture that looks like this. So everything goes up on both sides, which means that this limit from one side or the other or both is simply infinity. The third example would be the one that gives me minus infinity, as you might expect. And I can make that work from this previous example by just putting a minus 1 on the top and leaving the denominator the same. So q of x is the same here. Now p of x is a constant still, but now it's a negative constant. And so this will give us negative infinity and the associated picture. And that should be a dotted line. So let's draw a dotted line. If this is a, will be something like this, where it is simply the flip over of this because all we did was put a negative 1 there. Remember, all these case 2 examples have p of a, the top, not 0, but q of a, the bottom, definitely equal to 0. And in every one of these cases, you ended up with some sort of vertical asymptote. And the function could be minus infinity, infinity, or in the very first case, it could be minus infinity on one side and infinity on the other side. Now, what about case 3? This is the most unusual of them all, and the one that needs the most explanation. Suppose q of a, the denominator, is 0, and simultaneously the top, or the numerator, p of a, is also 0. So what does this seem to lead to? This seems to lead to x approaching a, the limit as x approaches a, of the rational function p of x over q of x. Apparently, and I'll put a question mark here because we don't know what this means, apparently it looks like it's going to 0 over 0. Now I'm very carefully putting that in quotes because we know 0 over 0 is not a real number. So although this represents some idea of what's happening, namely that the polynomial on the top as x approaches a certainly goes to p of a, which is 0 here. Likewise for the polynomial q of x on the bottom also goes to 0. But this certainly cannot be the result. This is what's called an indeterminate form. And it's called indeterminate because, well, we can't determine it. It's as simple as that. We cannot determine whether the limit exists, and remember, exists means equals a real number, whether the limit exists or not. And I'm not going to stop there because that would sound like we can't determine it at all. We can't determine it without more work. We actually will have to do something else here. Find some other argument so that we'll either end up with a real number or end up with plus or minus infinity, or know that this function has a limit on one side of a but not the other. But we do not want to end up with something that says in symbolic form, I don't know. We want to actually have meaning attached to this. So let's go ahead and look at some examples to see if we can see where we're going. Here is a straightforward example where 0 over 0 apparently is the result. Take the limit as x approaches 2 of x squared minus 4 over x minus 2. Again, the top is p of x, polynomial p of x. The bottom is the polynomial q of x. And please observe that both p at 2, which is the number the x is approaching here, and q at 2 are 0. If you put 2 in at the top, you get 2 squared minus 4, that's 0. The bottom 2 minus 2 is 0. So we have the conditions of case 3. All right, let me show you that we can actually compute this limit, even though it appears to be 0 over 0. And we're going to use algebra to make that happen. On the top, you might notice that the difference of two squares appears, x squared minus 4, and that can be factored into x minus 2 and x plus 2. The bottom remains very simply x minus 2. Now notice that this still appears to be a 0 over 0 form. But now x minus 2 over x minus 2 forms the number 1. And there's no difficulty in doing that because I'm not allowing 0 over 0 to turn up, because remember we're under the limit symbol. And the limit says x approaches 2, which means all along the way on that approach x is not equal to 2, which means x minus 2 is not 0. So whatever this number is, it's some real number that's not 0. And if I have that number over itself, that's 1. So this becomes the limit as x approaches 2 of x plus 2, because that's all that's left. And this is a polynomial. Substitution is what can happen here in polynomials. The x can be substituted for, the 2 can be substituted for the x. So we get 2 plus 2, and so we get 4. Aha! We have taken what was apparently a function that had a limit of 0 over 0, which was indeterminate, and yet we determined it to be 4. How did we do it? We did it in this step using algebra. And our knowledge that as x approaches 2, it's never equal to 2, so this cancellation, as it's often called, but it's really x minus 2 over x minus 2 is 1, that was allowed to happen, and because of that we were able to simplify this. Will this always happen? Will this always happen? No, unfortunately. What we've discovered here is one particular technique that if you have an algebraic expression with polynomials, you might be able to apply to end up determining this indeterminate form, as in this case 4. Let me show you one example of a function that we won't examine now, and its limit, that cannot be handled in this way. Algebra is insufficient. If you have the function sine of x over x as x approaches 0, what could that possibly be? It apparently is indeterminate yet again. The sine at 0 is 0, and of course x is 0. So this apparently is 0 over 0. Now, can we use an algebraic trick to somehow cancel the x into the sine x? No, we cannot. Algebra doesn't do it for us here. So if we are interested in finding this limit and determining it, we will have to find some other technique. And we will discuss this later, but for now we'll just have to leave that hanging as a mystery to be solved at another time. Now that we've looked at the limit of rational functions and the apparent appearance of that 0 over 0 indeterminate form, and we will see other indeterminate forms, by the way, now it's time to look at the cases where we look at limits of piecewise-defined functions. Now these are functions where one-sided limits make a large difference, so we need to pay attention to them. We've seen them before, but now we're going to look at a very specific example. So let's look at this example. Here is a piecewise function, and I will define it in 4 parts. One part I don't really need to mention, but it's good to have all of it there. So we'll say that this is 1 over x plus 2 for x less than minus 2. So this tells us what the domain is, and this is the functional value over that part of the domain. Then the function is undefined for x actually equal to minus 2. So at that point there will be no value of the function. Then it'll be x squared minus 5 for x bigger than minus 2 and less than or equal to 3. And then it'll be the square root of x plus 13 for x greater than 3. Well, before we go ahead and look at a limit here, I really feel much better myself if I have a picture of the function, especially when it's in all these different pieces, so that I have a sense at least of what's coming up. Now, strictly speaking, we could answer questions about the limit using only the given algebraic form of the function. But it's helpful and often wise, and something students don't do enough of, to draw pictures. So, what we'll do here is graph this function. So here are our axes. And starting from the top, it looks like minus 2 is a point of interest. So let's go ahead and mark minus 2. And we have 1 over x plus 2. Now at minus 2, the bottom here is 0, so this is undefined. And we know it has an asymptote, a vertical asymptote there. So let me go ahead and mark that in. Because remember, this is 1 over x shifted left by 2. And if that's 1 over x, then the graph of that to the left is just that function there. Now it's undefined at x equal minus 2, so I won't draw anything on the minus 2 line. And then x squared minus 5 is a very familiar one. X squared is just the standard parabola with its nose down here at the origin. And this is shifted down by 5. So that means that if we mark off 1, 2, 3, 4, and 5 here, the parabola will go down this far. And then let's just get a better handle on where it goes. If it comes up to minus 2, now it's not defined at minus 2, but we can figure out what the value would be there. That would be 4 minus 5, so it would be down here at a height of minus 1. So I can put a hole there and start my parabola going down like this. And at its other end, 3 is included. So if I put 3 in here, 3 squared minus 5 gives me 4. So I come up here to 4. And so I will have a value of the parabola at 3, 1, 2, 3, at a height of 4. And so I can go ahead and run the parabola up like this. And since this is a piecewise function, it actually ends there. Then for x greater than 3, the function is this square root function. Now if you look at this, you realize it's just the familiar square root of x function shifted left by 13, which means somewhere very far to the left, it just sweeps up like this. So that means the part that we have here will sweep something like that. So now we have a picture of this piecewise-defined function. We'll come back to this, but this at least gives us a sense of what the picture looks like. So now we can ask some interesting questions about the limits. We won't just find limits everywhere. What we'll do is we'll find the interesting limits. Now what do I mean by that? The interesting limits are those that are going to occur where the breaks, here's the picture of the function again, where the breaks occur, where the function is broken. Because in between the breaks, for example at x squared minus 5, that's a simple parabola. We know what that looks like and what its limits are going to be. What we don't know is what happens when these pieces meet. So we're going to look at minus 2 and 3 and examine the limits there. So we'll be looking for the limit of this function as x approaches minus 2, and we'll ask what the limit of this function is as x approaches 3. Now, it may happen that at one or both of these, the two-sided limit, which is what I've written, does not exist, but the two one-sided limits may or may not exist. It's always best in a problem, even if it's not asked, to go ahead and examine the two one-sided limits, because it may turn out that one or both of them will exist, whereas the two-sided might not exist. And you want to gather as much information as you can about functions, so always look for that. So we're going to examine these two, or the corresponding one-sided limits as needed, and we'll see how those go. So first let's focus at x equals minus 2. Now once again in the picture, here's the picture. At x equals minus 2, we see what it looks like. From the left, the function seems to be going down. From the right, it seems to be going up and not having a value there. It certainly does not look like, it does look like, in fact, that things are interesting here. It does not look like the function meets. So let's see what we learn from the limits. Certainly, we're going to have to examine the two one-sided limits. So for x less than minus 2 here, if we take the limit of the function as x approaches minus 2 from the left, remember that symbolism, that is going to be the limit as x approaches minus 2 from the left. What is the functional value to the left? If you recall, it's 1 over x plus 2. And then as x approaches minus 2, no matter what side you come from, 1 over x plus 2 is going to go to infinity because the bottom is going to 0. The only question is whether it's positive or negative infinity. So we know that it is one of the two infinities. Let's see if we can determine the sign. Well, if we're approaching minus 2 from below, that means we're approaching minus 2. We might draw ourselves a little picture here. We're approaching minus 2 here. We're passing through minus 4, minus 3, all the way down to minus 2. Well, that means these numbers here are bigger, although they have negatives in front of them. And so if I took negative 3 or negative 4 in here, I would get a negative number. So it seems like as I am approaching minus 2, the x value causes this expression to be negative. which means that this will be negative infinity in the end. So that's the way you tell if it's positive or negative infinity. It's not enough to know that the bottom just goes to 0, but you have to determine what the plus or minus sign of this is. Okay, well that's for x less than minus 2. What about the other direction? For x greater than minus 2, the limit of this function, x approaches minus 2 from above, there's that notation, is the limit as x approaches minus 2 from above. And what was the function above? Let's go back here and look. At minus 2 it was nothing. Above minus 2 it was x squared minus 5. So this is the limit of x squared minus 5. Now that's a particularly easy limit to take because we already learned that for polynomials taking a limit is the same thing as substitution. So if I put minus 2 in for x squared, I get 4 minus 5, so that's minus 1. And please note that these two, the two one-sided limits at minus 2, are not equal. And because these two are not equal, there is no two-sided limit. So we'd write the limit of f of x as x approaches minus 2 does not exist. However, we did learn that the two one-sided limits exist, and we found out what they were. So our work was not without merit. All right, that was the interesting limit at minus 2. Now let's go to the interesting limit at 3. At x equal 3, we perform a similar set of calculations. For x less than 3, we'll have the limit of this function as x approaches 3 from below. That will be the limit as x approaches 3 from below of, if you remember, the function is x squared minus 5 for x less than 3. And again, because this is just a polynomial, we can put the 3 in here. 9 minus 5 gives us 4. Then, in the other direction, for x greater than 3, we take the limit of this function as x approaches 3 from above. That is, in this particular case, the limit as x approaches 3 from above of, well, let's go back. Let's see what that function said. Here it is. For x greater than 3, the function is the square root of x plus 13. So that is the square root of x plus 13 in here. And as x goes to 3, this becomes 16 in here, and the square root of 16, as you know, is 4. These two are equal. So we can conclude in this case that the double-sided limit, the two-sided limit as x approaches 3 of f of x equals 4. That is to say, it does exist. So, when examining this particular function, and here's the picture one last time, we saw that the limit does exist. If we come from the right or from the left at 3, we do get a limit. If we look at minus 2 coming from the left, it goes down to negative infinity, and we found that out. It comes up here and seems to be headed toward a height of minus 1, and these two values don't agree, so that there is no two-sided limit here. All right. Now, let's see if we can summarize. The first thing you want to remember, which I've already mentioned, and that we've said before, is that two-sided limits exist if and only if both one-sided limits exist and are equal. Now that's something we did before, but it's good to remember that now. So if we have a two-sided limit that seems to be giving you difficulty, look at the one-sided limits, see if you can show they're equal or not. Then, the other point I wanted to make here is that one-sided limits are absolutely crucial to understand these so-called piecewise-defined functions. Because these functions are made up, as their name suggests, of pieces. And to understand what's happening where these pieces join or don't join is to look at the one-sided limits and draw your conclusions from that. Now we're going to stop for a moment, and then we'll do some exercises. on limits. Now it's time for some exercises. So let's start with this one. Find the following limit. It's the limit as x approaches 2 of the following rational function. It's x squared minus 4x plus 4 on the top and x squared plus x minus 6 on the bottom. So I will stop now, give you a chance to try this on your own. Now let me show you how I solve this problem. First of all, I just want to note that we have a rational function, so there's a polynomial p of x, say, on the top, and a polynomial q of x, say, on the bottom, and those were the notations we used earlier, so I wanted to make sure we were clear on that. Now, let's go ahead and see how the solution might come about. The first thing I want to observe is that when I was examining this earlier, I was worried about the case where q of x was 0. That was division by 0, which caused difficulties, and I had to deal with it. Now in this case, let's go ahead and discover whether when x equals 2 we have that problem arising. So we'll observe the following. If I take p, the upper polynomial, and I substitute in 2, I get 2 squared minus 4 times 2 plus 4. That is 0. Okay, that's fine, no problem there. Now let's look at the denominator where problems might arise. If we put 2 in for q, we get 2 squared plus 2 minus 6. That is also 0. So, what does that mean? That means we have what we called a 0 over 0 indeterminate form. That is a form that is not determined. That's why it's called indeterminate. And so what did we say in that case? Needs more work. So that means that we cannot take this limit immediately. We have to do some algebra if we're lucky, and in this case we can use algebra, or in other cases we can't, but we'll need to do more work before we can come to a conclusion. As it stands, we cannot determine a conclusion because this is an indeterminate form. So why don't I take this to the next page so we can work this out with a little bit more space. So here's the limit as x approaches 2 of this function x squared minus 4x plus 4 over x squared plus x minus 6. Well, the first thing I'm going to try, because it looks possible on the top and the bottom, is I'm going to factor. That seems to be a reasonable technique at this point, so let me give that a try. And factoring, of course, doesn't always work, but when it does, it makes things nice. So the top, it looks like we'll factor into x minus 2 and x minus 2. The bottom will factor into x plus 3 and x minus 2. Well, that's interesting. I have x minus 2 on both the top and the bottom. And I remember my limit theory that as x is approaching 2, x is never equal to 2. And because it's never equal to 2, that means x minus 2 is never 0. So this number on the top and the one on the bottom are non-zero. One over the other gives you 1. They're gone. So this gives you the limit as x approaches 2 of x minus 2 over x plus 3, and that's all that's left. Now we'll go ahead and try putting 2 into the limit, because that's our first choice when it works, and in this case the top gives me 0 and the bottom gives me 5. Well, of course that's 0 and I'm done. That was easy. I might suggest one other thing to you, just a suggestion. If you have the opportunity, whenever you're doing these limit problems, take a moment and graph the function. Because if you graph it, then you can actually go ahead and visualize, as I did when we were developing limits, what is actually happening as x is approaching 2. So you can see that it's heading to a height or a y value of 0. That's good for your insight and practice. All right. Let's look at a second exercise. Here's one. Find the limit as x approaches 3 from below, that's what that symbol means, remember, of the following function. 1 over the absolute value of x minus 3. Now that looks a little complicated, but give it a shot. Try it on your own, and I will come back in just a few moments and show you what I did on this problem. How I attacked this problem. Solution. First of all, there's more than one way to solve this. So I'm going to give you two different ways of solving it, and maybe one of them will coincide with what you did. Or maybe you'll have a third way that I didn't do. So here's one possibility. Let's observe the following. We are approaching x. X is approaching 3 from below. But let's just say as x approaches 3 from either side, that is from below or above, then the bottom, the expression x minus 3, approaches 0, of course. So that means the entire expression without the absolute value for the moment has to approach, if the bottom is approaching 0, this expression has to approach one of the infinities. So it's either plus or minus infinity. I know that immediately just by looking at the picture, not even paying attention to which direction I'm coming. Now, we do have an absolute value in there, so we can't ignore that. In this case, all that happens is, instead of worrying about x minus 3 possibly going to negative infinity, causing this to go to negative infinity, because we have absolute value here, 1 over the absolute value of x minus 3 is going to go only to positive infinity. So we solved that without very much work at all, just kind of realizing that if the bottom goes to 0, the expression is going to have to go to infinity. Now, what is a second way to do this? Well, let me draw a picture for you here. And that is the second way, actually. The other way is to use the graph to draw a conclusion. Now, if you're doing limits by hand, using the graph is not going to satisfy any question that you may have. You have to do it by hand and check the technology, check the technique that you've been playing with. But if you do use the graph, you'll have something to verify what you're doing. So, 3 is the difficulty. That's where the function does not exist. Here we'll just first look at the function 1 over x minus 3. And if you realize this is 1 over x shifted to the right by 3, then what we have is this kind of a curve. And then if we throw in absolute value, so we have 1 over x minus 3 absolute value, which is the same thing over the whole expression as it is just over the denominator, we end up with, well, let me draw my picture down here. Still 3 is the problem point. What has happened? Well, the part that was already positive in the y direction is still positive. But the part here that was negative with absolute value now flips upward. So the graph now looks like this. And you can see from this picture that what height is this function approaching as x approaches 3 from either side, although we were only interested in the left, the function's going to infinity, as we found out. So there's the second way to solve this problem. And you have probably a third way that you may have come up with. Well, let's look at a third example here. Let's let this function, let's take a piecewise defined function. T squared in one part, t minus 2 in the other part. It'll be t squared for t greater than or equal to 0, and t minus 2 for t less than 0. And of course that covers the whole real number line. Here's what I'd like you to try. Find the limit of g of t as t approaches 0. And remember, if this two-sided limit doesn't exist, check both one-sided limits and see if they exist. And we'll at least get some information about this problem. So give it a try, and I'll be right back. Well, here's my solution. Solution. Now, since this piecewise defined function breaks at 0, I'm going to examine the two one-sided limits on either side. Now, if I'm lucky, they will be equal, and I'll have a two-sided limit, and I'll be able to answer this question with a specific number. If not, at least I will know that from the left and right, certain limits exist. So, for t less than 0, the limit of g of t, as t is approaching 0 from the left, so I want to approach 0 with the little minus sign up there. What is that specifically? As t approaches 0 from the left, g of t from the left is t minus 2. So it's t minus 2, and again with the polynomial I can just put the number in. That simply becomes minus 2. On the other hand, and the other direction, for t greater than 0, the limit of g of t as t approaches 0 from above is equal to the limit as t approaches 0 from above of the other part of the function, t squared, because it's defined there for t greater than 0, t squared, and t squared, when you put 0 in, gives you 0. These two, of course, are not equal, so that means immediately that the two-sided limit does not exist. So I could write here does not exist. I have gained the knowledge that the left and right limits are these two numbers, and that this does not exist. But you may have noticed something here. Did you notice when I wrote t greater than 0, but that the function is actually defined t greater than or equal to 0? Well, with t equal to 0, the function is going to have the value t squared, so I can gain one more piece of information. Note that although the two-sided limit fails to exist, the function actually has a value at 0. G of 0 is 0 squared, because at 0 it's the t squared function, which of course is 0. So g of 0 equals 0, which does exist. So we have the interesting case of a function whose left and right limits exist, whose two-sided limit does not exist, but which does have a value at that point 0. Let's go ahead and look at a picture of this, because that sounds interesting enough. So this is a graph of this exercise number 3, and it's a very simple graph. We can go ahead and quickly sketch this out. It is the function t squared, so this is the t-axis, so this is g of t equals t squared, where t is greater than or equal to 0. That's why I included this point in the middle. And then on the other side, if you remember, g of t is equal to t minus 2, and that's for t less than 0. Well, t minus 2 is the 45-degree line. That would be t, shifted down by 2. So here's minus 2, and so we start here and go off this way. There's our picture. You can see that the two one-sided limits do not agree, but there is a value of the function here at 0. And of course, there's no two-sided limit. So with that, we'll stop our exercises here and move on to a little more calculus. Now to continue, we'll look at the algebra of limits as x approaches plus or minus infinity, as you see up there on the screen. Before, we looked at where x was approaching a real number. Now we want to know what happens to functions as x goes far to the right, the plus infinity, or far to the left, the minus infinity. That's why we refer to this as end behavior, where the ends are far to the left or far to the right. So the first thing we'll do here, just as we did with the x approaches a case, we'll first look at basic limits. So let's start with a few of these. The first one, as usual, is the constant function. That's our very familiar and easy function. This is where f of x equals some constant. I'll just use k to indicate a constant here. And in that case, you remember what the graph looks like. If the k is positive, for example, in this picture, then the graph is simply the horizontal line at the height k. So you might guess as x goes to infinity, or as x goes in the other direction to minus infinity, what happens to the function? Well, nothing. Nothing ever happens to a constant function. It's constant, after all. So that would be the limit of k as k approaches minus infinity is equal to just k, and likewise the limit of k as k approaches plus infinity would also just be equal to k. So there's nothing very interesting there. We just want to get this down so that you realize it. Now let's look at a more interesting function, the identity function. And this is one we've seen before too. This is the function that doesn't do anything to x. So f of x equals x. It is identically the same as it was when it went into f. And this function again is one that we know well. It's just the 45-degree line passing through the origin. And as x goes to infinity, we can see that this function is going upward to infinity, just as x is. And as x goes to negative infinity, we see that the function is going downward to negative infinity, just as x is. So that tells us, as if you couldn't guess, as x goes to minus infinity, what does the function x go to? Well, minus infinity, of course. And the limit of x as x goes to infinity equals infinity, likewise. So this was another one that's easy. Well, of course, these are called basic limits, so we expect them to be easy. All right, let's go back to one of our favorite functions, sometimes called the reciprocal function, or if you like to be a little more colloquial, the flip-over function. And that's the function f of x equals 1 over x. Again, a very, very familiar picture. We talk about this function a lot. It has this kind of a picture. And here, as x goes to infinity, we can see what's happening. The height of the function is going downward. It is going down toward this height, which is a height of 0. Then, as x goes to negative infinity in the other direction, the height is going upward, of course, but it's going upward again to the same height, the height of 0. So this is approaching 0 from above. This is approaching 0 from below. So that's worth mentioning. The limit of 1 over x as x approaches minus infinity is equal to 0, and I'll go ahead and mention from below. And likewise, the limit of 1 over x as x approaches infinity, that's far to the right, approaches 0, but this time it approaches from above. Now, keeping these in mind will help you as you do graphs many times in this course. So it is true that both of these simply go to 0, but it is also helpful to know that one of them is going from below, that's the one at the left, and the one at the right is going from above. So that's it for basic limits. Now we'll move on to a little bit more complicated limits. Now we're going ahead and look at limits of sums, differences, products, quotients, and roots. We did this when x was approaching a real number, and now we're going to do the same thing for x approaching one of the two infinities. So what we're doing here is we're taking the rules of algebra for limits that we looked at previously and now applying them to the case where x is approaching either infinity or x is approaching minus infinity. So these are going to look very much alike, except in a couple of cases they're almost identical. Just as a note, we only state these for the x approaches infinity case, because the other case is the same, and it is not worth our time to go ahead and say both of them. I think you'll see that even the infinity case echoes the x approaches a case. So there's a lot of repetition here. And as before, we will suppose that what we have are given two limits. The limit of f of x as x approaches infinity, we'll call that L1. And the limit of g of x as x approaches minus infinity, we will call L2. And that will give us a reference as we do these rules. So we'll do them in order. First, we'll say what is the limit as x approaches infinity of the sum of these two functions. Well, just as before, it is the sum of the two limits. And the two limits were L1 and L2, so this becomes L1 plus L2. The limit as x approaches infinity of the difference is exactly the same format. This would be L1 minus L2. The product, luckily for limits, the product is very straightforward. The limit of f of x times g of x is the limit of f of x times the limit of g of x. And the limit of f of x is L, the limit of g of x is L2, so this is L1 times L2. Now, the product, as we saw the last time, also has a few special cases that are worth mentioning by themselves. The first one is if you take the limit as x goes to infinity of k times f of x. This is where one of the members of the product is actually k, a constant. Then because this breaks up into the limit of the first times the limit of the second, and the limit of k is just k, this amounts to the fact that a constant simply comes in front of the limit. You can pull it out front. As long as it is multiplied times the other function, you can simply push it out front like this, and that saves you a lot of work later. You use this a lot. Now, there's another case that's of interest. What if the factors here are repeated? So, for example, as I showed you before, if you take the limit as x goes to infinity of f of x to the fourth power, that's the same thing as taking the limit of f of x as x goes to infinity all to the fourth power, because the limit of the product is the product of the limits. The limit of this product is the product of all of these limits. And each one of these limits is L1, so this becomes L1 to the fourth. Now there's one other that's very interesting and follows from the product rule for limits, and it's this case. This one we use a lot. Suppose you have 1 over x to the nth power. Then, since this is a function to the nth power, the same product rule holds. This is simply the limit of 1 over x, which we know, all taken to the nth power. Now the limit of 1 over x as x goes to infinity, we know, goes to 0. We just did that. So this goes to 0 to the n, hence 0. So if you have 1 over x to the n, the limit of that as x grows very large, or in fact as x grows very small to negative infinity, will always be 0. Very handy in some of the limits we'll be seeing coming up. Now, let's go on and finish our arithmetic operations here. The limit as x approaches infinity of a quotient, we haven't done that one yet, is, just as in the case of multiplication, the limit of the top over the limit of the bottom. So the limit of the quotient becomes the quotient of the limits. And in this case, the upper limit is L1 and the bottom limit is L2. Now here, of course, we have to have the usual proviso, provided that L2, the denominator, is not 0, because we can't divide by 0. And finally, in our arithmetic operations, we want to know what happens when you take roots. And this is exactly what you would expect also. If we have the nth root of f of x and we want the limit as x goes to infinity, then that's going to give us the nth root of the limit of f of x as x goes to infinity. And since L1 is the limit of f of x, this becomes the nth root of L1. And again, there is a proviso here. We have to make sure that L1 is a number that you can take the nth root of. So, provided when n is even, that's the only problem case, then in that case, L1 is greater than or equal to 0. So that covers all of the arithmetic operations. Now there's one other one here as x goes to infinity that's interesting. And interesting means, of course, that we'll be using it more than once. Let us just consider this case. The limit of x to the n power as x goes, well, we want to look at x going to infinity and x going to negative infinity. Well, first look at x going to infinity. What is happening? X is getting larger and larger in the positive direction. So x is eventually positive, And so whatever n is, this is going to be a positive number that's growing, which means this should go to infinity, and it does. And this is true for all values of n equal 1, 2, 3, 4, and so on. So maybe that's not particularly interesting. Powers of numbers where the number is getting larger in the positive sense, that those powers go to infinity, perhaps doesn't surprise you. But now let's look at the other direction. Let's take the limit of x to the n, the same function, as x approaches minus infinity. Now, if you think about this, something happens depending on what n is. If n is even, negative numbers are made positive. If n is odd, negative numbers are preserved, or at least their sign is preserved. So that means we have two cases here. We get minus infinity for all of the odd numbers, n equal 1, 3, 5, and so on. In other words, I'll write the word odd here. We get infinity for n equal the even numbers like 2, 4, 6, and so on. These would be even numbers. So when x goes to one of the two infinities, x to the n does go to an infinity. But if x is positive, if x is approaching positive infinity, it'll go to positive infinity. If x is going to negative infinity, it oscillates back and forth depending on what happens to what form the n takes, if the n is odd or even. So, since it alternates depending on the n, what would you say about this limit if I talked about this limit and mentioned all of the n's? Then you would have a limit that oscillates between two values, which means it does not exist. So, does not exist if all n are allowed. So, you have to be careful when you're going to negative infinity. That is the lesson here. And finally, these are such interesting limits. Let's look at their graphs and just make a silent observation of these graphs. I will go ahead and draw 6 graphs, and then we'll move on to some other limit properties. But I think you'll see from these that what we just learned on the previous page makes perfect sense. Here is the graph of x, odd power. Here is x cubed. X cubed, of course, looks like this. I drew the x again. Well, that's all right. The x cubed looks like that. X to the 5th flattens out a bit. X squared, as you know, looks like this. X to the 4th looks like this. X to the 5th flattens even more. And notice that as we go to the right in every one of these, the function goes off to positive infinity. But as we go to the left, it depends. In the odd cases, it goes to negative infinity. In these even cases, it goes up to positive infinity. So with that quick observation, we can move on. Now let's put some of this together and look at the limits of polynomial functions. And they have 2 types of n behaviors, and only 2. So let's see what I mean by that. First of all, let's go ahead and write out a polynomial function so we're all talking about the same object. A polynomial function. What does that look like? Well, let's call it f of x. It's going to be cn x to the n plus, say, cn minus 1 x to the n minus 1 plus ... down to c1x plus c naught, where, in order that we are talking about something that's not nonsense, the leading coefficient cn is non-zero. As usual with a polynomial, these are the powers of x. The n here is the highest degree of any power of x, and so it's called the degree of the polynomial. We'll use that fact later. And all of these other cn's, which are subscripted by n, n minus 1, all the way down to 0, are simply real numbers. Now, what are these two end behaviors I'm referring to here? Do I mean x going to plus or minus infinity? No. I want to talk about the end behavior of the function. So I'm interested in what happens to f of x. And I'm saying that f of x itself has two end behaviors. So let me write down what I mean by that. The two end behaviors are that as x goes to infinity, which is the rightward end, make sure we're talking about the right ends here, or as x goes to minus infinity, which is the leftward end, again there's the end, then, as I said, it is the functional value that we're interested in. F of x goes to infinity, or f of x goes to minus infinity. So these are the two possibilities that I mentioned above in the title of this section. The functional value can go to plus or minus infinity, and that is all, as x is going to plus or minus infinity. So those are the two possible end behaviors for a polynomial. But we can say more than that. We can get much more specific. But we can say more. Observe the following. Now this is not a complete proof, but it's a plausible argument. Here's f of x, our polynomial function. Cn x to the n plus Cn minus 1 x to the n minus 1 plus down to C1x plus C naught. Now observe that if I factor out x to the n here, kind of an odd thing to do, but let's just do it and see what happens. If I take the xn out, I'm left first with Cn, that first step is easy. Then what happens here? Well, if you look, you're left with Cn minus 1 over x. Because if I multiply the xn back in, then x to the n over x would give me x to the n minus 1. Continue down doing this. You have C1 over x to the n minus 1, and then finally C naught over x to the n. Now, why would anyone do this? Well, notice that all of these terms with an x in the denominator, as x goes to infinity, each one of these terms will go to 0. So let's write that down. As x goes to either one of the infinities, so I'll write plus or minus infinity. When you see this, you have to read it plus or minus infinity. It's simply shorthand. As x goes to plus or minus infinity, these terms I have marked, these terms all go to 0. So that suggests that whatever is happening to this polynomial function is essentially the same thing as this Cn times x to the n, because all the rest of this in the end goes to 0, or, as we like to say, becomes negligible. So let's write that down. So the end behavior of this function, this polynomial function, f of x, seems to match the end behavior of that other much shorter and much easier function to deal with, the end behavior of Cn times x to the n. It's just a nice single term. This is much simpler. So, let me take this argument and go ahead and encapsulate it in a theorem so that you'll remember it. That's what we do in mathematics. After we've discovered something, we put it in the form of a theorem so we can write it down and remember it. I won't do the proof of this. As I said, I gave you a plausible argument. As x goes to plus or minus infinity, this is actually two cases in one. If I have the polynomial in here, Cn x to the n down to C1x plus C naught, that limit is the same thing as the much simpler limit as x goes to plus or minus infinity of Cn x to the n alone. Now see how much nicer and easier that is? So in practice, if you're asked to take the limit of any polynomial whatsoever as x goes to one of the infinities, you can ignore everything except for the highest power of x. That will totally determine what the limit is. Now that must make things much easier. Here's an example. If I take the limit, and let's go to minus infinity, say, of this particular polynomial, minus 4x to the 8th plus 17x to the 5th plus 3x to the 4th, you can just make your own up, plus 2x minus 50, then I know from this previous theorem that I can ignore all of this stuff to the right and just concentrate on this highest power. So this is the same as the limit as x approaches minus infinity of just minus 4 times x to the 8th. Well, from my previous knowledge of limits, I know that if I have a constant here, I can pull that out in front of the limit. So this becomes minus 4 times the limit of x to the 8th as x approaches minus infinity. And since this is an even power, although x is approaching negative numbers, when you take those negative numbers to the even power, they will always be positive. So this is growing without bound in the positive direction. So this part goes to positive infinity. However, it is multiplied by a negative number, so the end result is negative infinity. And this was made much simpler because all this part here could be simply ignored, because in the limit, only the highest power matters in a polynomial. That is to say, the highest power is what we say dominates the limit. And so, leaving you with that, we'll move on to rational functions. Now it's time to look at the limits of rational functions. And they have three types of end behavior. And that will be interesting to examine. Now this is as x goes to plus or minus infinity, of course. So first of all, just to start us off correctly, let's remember that a rational function has the following form. It's a polynomial over or divided by another polynomial. If you write it in notation, we could say that the rational function f of x is, say, p of x. We've used p of x and q of x for polynomials before. P of x over q of x. And we can refer to p of x as the top polynomial and q of x as the bottom polynomial. Now, of course, technically we could call those the numerator and the denominator, but I'd rather just call them top and bottom. It's a lot easier. Now remember, the degree of a polynomial is the exponent of the highest power of x in the polynomial. So, you know that a polynomial is a sum of various terms with powers of x. Simply take whatever number is the highest power. That exponent is called the degree of the polynomial. Now, we will be using that fact as we try to find out what happens when we take the limit of a rational function as x approaches plus or minus infinity. What could possibly happen? Well, it turns out, as I mentioned, that there are three types of behaviors. And they're all end behaviors because we're looking as x goes to plus or minus infinity. That's to the left or right. And those are the ends of the function in our sense. All right. There are three cases. A polynomial on the top and a polynomial on the bottom have different degrees, possibly. So let's suppose the degree on the top equals the degree on the bottom, rather than having them different. Now that means our rational function has the same degree of a polynomial on the top and the bottom. It's either quadratic on the top and bottom, or cubic on the top and bottom, and so on. What happens then if we want to find the limit as x approaches one of the infinities? Well, we're going to do these by example because it's easier to make the point that way. So let's, for this one, take an example. F of x equals the following function: minus x over 7x plus 4. Now, notice that both top and bottom have the same degree. And in this case, that degree is 1. They're both linear. All right. What happens now if I take the limit of this function as x goes to, and I can just look at one of the infinities because the idea will be the same for both. So I'll just let x go to plus infinity. And so I have the limit as x goes to infinity of this expression, this rational function, minus x over 7x plus 4. Now, how am I going to discover what happens here? Here is the first intuitive problem. If I let x go to infinity, as I try to do with other functions where the x is approaching a real number, you try and put that number in there to see what's happening before you wonder if there's any other work. If you try that with infinity here, look what happens. You get an infinity of one type or the other on the top, and on the bottom you get another infinity, which means you've got this indeterminate form, infinity over infinity. Now, that's not a real number, so that signals, because it's indeterminate, it signals that we need to do something else. So here is a very standard technique that will allow you to see what's happening here. If you divide top and bottom by whatever that common degree is, that is 1 in this case, if you divide by the power of x that has that degree, in this case just x, watch what happens. We take the limit as x goes to infinity. On the top now, by dividing by x, we're left with minus 1. Well, that's nice. On the bottom, we divide 7x by x, we're left with 7. And then when we divide 4 by x, well, we get 4 over x. But you know, although that looks complicated, it's not as bad as it seems. Because observe, there's only one x now left in this expression. And it's in this expression 4 over x. Well, what happens to 4 over x as x goes to infinity? We already know the answer to that. This expression goes to 0. Which means I now know how to take this entire limit. This part goes to 0. I'm left with minus 1 over 7, which is exactly what this limit turns out to be, minus 1/7. And the way to remember this is to remember that the end result, notice from the very beginning, that minus 1 is the coefficient of the highest power of x here. 7 is the coefficient of the highest power of x here on the denominator, or the bottom. So I didn't have to do all of this work, and in the future you won't have to either. Because you've seen this work, if you have a rational function where the top and bottom have the same degree, then all you have to do is ignore everything else and just take the coefficient of the highest power on the top and the coefficient of the highest power on the bottom, and look, you have minus 1/7, just as we got here. And we can say that more specifically by saying the leading coefficient of the top is then over the leading coefficient of the bottom. And leading coefficient always means the coefficient of the highest power of x. That's what leading means. Now, let me note one other thing while we're at it. Remember, when you're taking the limit of a function like this, the function represents y values, the vertical values. You're asking what vertical value is the function f of x approaching as x approaches infinity? Well, it is approaching this vertical value of minus 1/7. In other words, y equal 1/7 is a horizontal asymptote. Remember, we talked about these before. A horizontal asymptote for this function. So there's more here than meets the eye perhaps, but we won't have to do all of this work in the future because we now have developed a technique that will take us immediately to the limit, provided the degree of the top and the bottom are the same. Now, what if that's not the case? Well, that leads us to type 2. Oh, these names, by the way, type 1, 2, and 3 are non-standard, so in other books they may be listed another way. But here we'll just go ahead with this way. Suppose the degree of the top is strictly less than the degree of the bottom. The previous case was where they were equal. Now let's look at where they are different and the top has degree less than the bottom. Again, I will make my point by looking at an example. In this case, let's take this easy one, 5x plus 2 over 2x cubed minus 1. Notice that the degree of the top is equal to 1. It's linear. The highest power of x is 1. And likewise, the degree of the bottom is 3. It is a cubic down here. so the highest power is 3. And notice that the top is less than the bottom, as we wanted to look at in this case. Now we'll ask the same question we asked before. What happens if you take this limit as x goes to infinity? Take the limit as x goes to infinity of this expression, 5x plus 2 over 2x cubed minus 1. Again, the first intuitive step gives us the same indeterminate form. If we try to put in infinity, of course infinity is not a number, but if we tried to put it in, we would get infinity on the top and infinity on the bottom. An indeterminate form, which means nothing. We have to do more work to see what this limit is. So we're going to use exactly the same technique. We will divide top and bottom by, well, now we have to make a choice. Last time the degrees of the top and the bottom were the same. In this case, the top and the bottom are not the same. So which one do we divide by? Always divide by the higher of the two. Divide by, in this case, x cubed, because 3 is the higher degree of the two. Now, let's see what happens here. We have the limit as x approaches infinity. On the top, if we divide by x cubed, we get 5x over x cubed. That's 5 now over x squared, plus 2 over x cubed. The bottom, we just get a 2 in the first place. That's the only place the x cubed will cancel. Minus 1 over x cubed in the second place. Now notice again, if I look at all these expressions that involve an x in the bottom taken to a power and a constant on the top, all of these expressions go to 0 in the limit, which means I'm left with 2 on the bottom and 0 on the top. Well, that's a perfectly well-defined real number. That means I have 0 as my limit. This will always work. This is always going to be 0. If the degree of the top is less than the degree of the bottom, then the limit of the rational function as x goes to infinity or minus infinity will always be 0. A colloquial way to think about it is, both of these expressions, the top and the bottom, are going to infinity, but the bottom gets there first. The bottom wins the race, so that means it takes it to 0. And now again we have a technique that takes you from this top to the bottom without having to do any work. Immediately, as soon as you recognize that the top degree is less than the bottom and you're taking a limit as x goes to infinity, you know that the answer is 0, period. You don't have to do any of this work now. That's the advantage of doing this here. We are now going to save ourselves trouble. And since we started looking at horizontal asymptotes, let's go ahead and again and remind you, the y value is what the limit is taking. That y value ends up being 0, so that means y equals 0, which is just the x-axis, by the way, is a horizontal asymptote here. Just as in the previous case, we had another horizontal asymptote. All right, now we've dealt with the case where the degrees are the same. That was the previous one. Here, where the degree of the top is less than the bottom, well, there's only one more case. Let's take a look at it. And I'm calling this one type 3, of course. This is the case where the degree of the top is greater than the degree of the bottom. And in this case, it is also going to be very easy once we get done. Here we have f of x as our example. Say x squared plus 4x plus 5 over x minus 1. Now notice that the degree of the top is equal to 2 here, and the degree of the bottom is equal to 1. And as we've said before, this is the example where the degree of the top is greater than the degree of the bottom. So let's see what happens as we take the limit as x goes to infinity once again of this function. So we'll have the limit as x goes to infinity of this rational function, x squared plus 4x plus 5 all over x minus 1. We'll use exactly the same technique. It worked before. Let's try it again. Let's divide the top and bottom by, and since here the degrees are different again, we'll use the same technique as last time. We will find the highest degree and divide by x to that degree, which is x squared in this case. Here's what happens. We end up with the limit as x approaches infinity of, now on the top we divide by x squared, we get a 1, that's the easy one. 4x over x squared gives me 4 over x, and then 5 over x squared is the last one. On the bottom I get 1 over x minus 1 over x squared. As before, everything with an x in the denominator and a constant on the top will go to 0 as x goes to infinity. What does that leave me with? That leaves me with a 1 on the top, so the top is a constant, but the bottom goes to 0. What has that meant in the past? What it's meant is that this expression is going to go to one of the infinities, and that's what happens here. In this particular example, I can actually be clear. It's going to either go to infinity or minus infinity. It'll go to infinity if x goes to infinity, as it is doing here. If I let x go to negative infinity, say, that would be the second case. I wanted to mention it, although it didn't occur here, because in general, that's what will happen to this kind of case. If the polynomial has a degree on the top greater than the bottom, the colloquial way to say it is that the top wins. The top goes to infinity faster, and so takes the entire expression to infinity with it. That's what happens. It'll either be infinity, as it is in this problem, or possibly minus infinity. You'll have to check in an individual case which is which. But it's always one of these. Always one of these. So, to sum up, what have we done here? In type 1, you recall, we had the degrees were equal, and then the limit was simply the coefficient of the common degree power on the top and the bottom. That gave us a constant, which was a horizontal asymptote. The next one, the bottom had degree higher than the top, and we got a limit of 0 in every case. In this case, we get a limit of infinity in every case. And which infinity will depend on the individual function. So now you know how to take the limit as x goes to either infinity of any rational function. There are only 3 possibilities, and you've seen them all. Now, as one final example of the sort of functions we want to look at as x goes to plus or minus infinity, we'll look at functions that involve radicals. That is to say, roots appear of some kind. And what I'll do here is do 2 examples to show you the standard kinds of techniques one can use here. So the first example, let's go ahead and take the limit as x goes to minus infinity of this expression. In this one, it is a fractional function with a radical at the top. And we want to find out some sort of technique to get at this. Well, we really have already seen the idea that will work. The idea is to try to find and create the appearance of 1 over x, or 1 over x squared, or 1 over x cubed, and so on. Because as x goes to infinity, those expressions all go to 0. So how are we going to do that here? We have a square root to deal with. Well, here's what we're going to do. If we divide top and bottom by the following. The bottom we'd like to divide by x. That is the highest power on the denominator, and that seems to be reasonable. Now, we'd like to do the same on the top, but we have to get inside the square root. But notice that the square root of x squared takes us back to x. It actually takes us back to the absolute value of x, because when you square something, you knock out any negative signs, and when you take the square root again, you will recover the positive version, but not the negative. So that means what we'll do is we'll divide top and bottom by the absolute value of x, which is the same thing as the square root of x squared. Little piece of algebra you should remember. Now I'll use it in different ways on the top and bottom, and let's see what happens as we move to the next step. We're going to take the limit as x goes to minus infinity, and now on the top and bottom we're going to have a fraction. The top will be the square root of x squared plus 2, and I will use the square root form, of course, here, and divide that by the square root of x squared. On the bottom, I will go ahead and divide by absolute value of x. in doing that, I can say one more thing. As far as the bottom goes, notice that since x is going to negative infinity, x is going through the negative numbers, which means I don't have any mystery as to what the absolute value of x is. X, since it's going to negative numbers, is negative. The absolute value of a negative number requires putting a negative sign in front of it. So the absolute value of x here is negative x. That makes this simpler on the bottom. I'm dividing by negative x. That will give me minus 3 here, plus 6 over x in my second place. Now let's take one more step to clean this up a bit. The limit as x goes to minus infinity. The top now can be written as a single square root. I'll divide the x squared into both parts, so I have 1 plus 2 over x squared. Then I have minus 3 plus 6 over x here, and I get the same kind of conclusion I saw before. If x goes to any one of the infinities, in this case minus infinity, 2 over x squared and 6 over x both go to 0. And I'm left with what? The square root of 1 on top and minus 3 on the bottom, so the final limit is minus 1/3. And again, this can be thought of as a horizontal asymptote to this particular more complicated looking function, but I won't write that out this time. So look what we did here. We divided the top and bottom by the same essential power of x. This is essentially x to the 1 power. It was absolute value because I wanted to divide by square root of x squared to get the top to work out. On the bottom, it turned out that I knew what the absolute value was. It's just minus x because I know which direction I'm going. So I simplified a little bit. But this is the same technique we use for the rational functions. It works very well here too. Now let's do a different kind of radical limit. If I take the limit as x goes to infinity of this one, I get something very different. X to the 6th plus 5x cubed, radical, square root in this case, minus x cubed. Now if you look at that with your intuitive grasp of limits, you say, well, I'm just going to see what happens as the x heads off toward infinity. This first expression heads toward infinity. The second expression also heads toward infinity. This appears to be infinity minus infinity, and you know what that is? That's another one of those indeterminate forms. We saw 0 over 0 as being indeterminate. This is another one. You cannot determine what this is without more work. So we need to find some algebra that we can do here that will allow us to find out what this limit is. This is a difference, and this difference suggests the technique that we're going to use. This is very standard for this kind of a problem. So I take the limit as x goes to infinity, and let me rewrite this. X to the 6th plus 5x cubed under the square root minus x cubed. And now I will multiply top and bottom by the same thing, so the net result is multiplying by the number 1. What will I multiply by? I will multiply by what's called the conjugate of this expression. That is to say, this square root plus x cubed is the conjugate. And so I will multiply by that. Now if you've seen this before, you know where we're headed. If you haven't, then I will show you what happens here. The advantage to this is certainly not in the denominator because we just gained a denominator where we didn't have one. It must be in this numerator or the top. So the limit as x goes to infinity, now what do we have? Well, we have that denominator because that's the only thing down there. X to the 6th plus 5x cubed under the square root plus x cubed. Now what happens to the top? Notice that you have a binomial difference and a binomial sum here. When you multiply those two together, you get the difference of two squares. This is a well-known algebraic result. The square, of course, of the square root is just x to the 6th plus 5x cubed minus the square of x cubed is x to the 6th. That immediately suggests a simplification, x to the 6th minus x to the 6th. So this becomes the limit as x goes to infinity of, the top becomes 5x cubed and the bottom remains the same. plus x cubed. All right. Now we're at the same kind of problem we were before. This problem started out with a difference which wasn't like the previous fraction we looked at. But now we have a fraction and we have a root. We're going to use the same technique we used before, which is to say we will divide top and bottom by, well, it looks like x cubed is the right thing to use. So let's go ahead and try x cubed, which can also be written, because we're going to want to get it into the square root here. Remember that x cubed is the square root of x to the 6th. Okay, let's see what step that leads us to now. The limit as x goes to infinity of, the top divided by x cubed just leaves us with 5. That's good. The bottom, on the right we're going to get just plus 1. We're dividing by x cubed. On the left we'll divide by x cubed in this form of square root of x to the 6th. That x to the 6th will then go and divide into each of these, leaving us with a square root of 1 plus 5 over x cubed. Well, that looks familiar. The 5 over x cubed goes to 0 as x goes to infinity. And then we're left with a number of constants, and the final result, of course, is 5 over, there's 1 plus 1 down here, that's 2. 5 halves, and 5 halves, just as in all the other problems, since this is a y value, this is the y equals 5 halves result, this is a horizontal asymptote for this function. So that gives you a couple of examples of how one might take the limit of radicals in a function where x is going to infinity. With that, we'll pause for a moment. Look at some exercises. The first one is this limit. Let's see what you can do with this. The limit as t goes to infinity of this rational function 5 minus 2t cubed over t squared plus 1. Give that a try. I'll come back and show you what I did. Here's my solution. First, I notice, as you did, that it's a rational function. And so what I want to do with a rational function is look at the degree of the polynomial on the top and on the bottom. The degree on the top is 3. It's a cubic. The degree on the bottom is 2. That's a quadratic. The degree of the top is bigger than the degree of the bottom. If you remember from our results, this should give me one of the infinities, either positive or negative infinity. The top wins. It outgrows the bottom. Now, the only question is which infinity? Is it positive or negative infinity? Well, that depends on the individual function, such as this one. So now we look at this. As t here in this case goes to negative infinity, notice that the denominator remains positive throughout because it's t squared. So this is positive, will not affect the plus or minus sign of the end result. The top, let's look at what happens to minus 2t cubed. T cubed will preserve the negatives, so that will remain negative. But since it is multiplied by negative, that will become positive. And then positive plus 5 is still positive, so this will tend toward plus infinity. And that's the only analysis you need to do for this problem. Let's look at another example. Let's take the limit as x goes to infinity of the square root of x squared minus 3x, that's a minus 3x, minus x. Go ahead and try that. So, did you see that this was one of those that is of that indeterminate form, infinity minus infinity, and probably involves that conjugate technique? Well, let's see. Here's what I did. If you do notice that as x goes to infinity, both of these expressions go to infinity, and you shouldn't worry about x squared minus 3x, because remember when we talked about polynomials, we said the end behavior of a polynomial is totally determined by its highest power. As x goes to infinity, x squared goes to infinity, sends this first term to infinity. And so it looks like this is infinity minus infinity again. The technique, multiply by the conjugate. So multiply top and bottom by the conjugate. So that gives us this. As x goes to infinity, let's write the original expression down here, minus x, and multiply now by the conjugate of that expression, which is this expression with a plus in the middle. So this is the square root of x squared minus 3x plus x. And the same thing on the bottom, so that the net result again is that this is 1. Doesn't change the expression that we're trying to work with. The advantage is that it cleans things up, we hope. We will now have the denominator, of course, will remain the same, x squared minus 3x plus x. But from our previous work we know that we have the binomial a minus b here, and this is a plus b, using the letters a to stand for these more particular terms. And that gives us the difference of two squares. So we get x squared minus 3x as the square of the square root, minus x times x, which is x squared. The x squared here and the x squared here, of course, add to 0. So this cleans up the top as x approaches infinity, and we're just left with minus 3x, and the bottom is x squared minus 3x plus x. Okay, now what do? The same thing we did before. We look for a power of x to divide by. Divide top and bottom by x equal the square root of x squared. And I write it both ways and realize you may think, oh, he did this wrong because he should have absolute value here. Well, you're absolutely right. I should have absolute value, but I don't need to because my x's are going to positive infinity this time. So they're all going to be positive as I get closer and closer to my destination. So these will be positive, so this is its absolute value. And I write this square root of x squared term because I want to get inside this square root here. So dividing top and bottom gives me, the top of course becomes minus 3, which is very nice. The bottom, I divide the x, I get plus 1 here. And then the square root I divide by the square root of x squared, the x squared goes inside. And I end up with x squared over x squared, that's 1 minus 3 over x. Again, I have a 3 over x, which will go to 0 as x goes to infinity, and nothing but constants left over. That leaves me finally with minus 3 halves, as I squeeze that in on the bottom of the page here, minus 3 halves as the limit I was trying to get to from the very beginning, which on the surface appeared to be this funny indeterminate form, infinity minus infinity. But in the end turned out to actually be minus 3 halves. So with that, we'll stop here. Now, as a last note on this section, as we look at the end behavior, we will now look at limits of the natural log of x, e to the x, and more, in particular the trigonometric limits. So let's take a look at this. The first thing is we'll look at the very first one that's listed there. The function is f of x equals the natural log of x. And you may remember this from the first sections that we did in this class, and the graph of the log function is something like that. It passes through 1 here, it has the y-axis as a vertical asymptote, and it grows off to the right. So this is the graph of that function, and you can see from that, although we won't walk through a proof of it, it seems, and is in fact true, that the limit of the natural log of x as x goes to infinity, which means goes to the far right, is going to be infinity. This, although it doesn't seem to be growing very fast, in fact does grow as high as you would like it to grow. And if you go in the other direction for the natural log of x, what happens then? Well, first of all, you can't go all the way to infinity because the function stops is not defined for 0 or any negative numbers. So we have to go as far as here. That means x would approach 0 from above. Remember that notation. And in that case, you can see from the picture that the log function is heading downward toward negative infinity, and that in fact is what the limit is. Now that's the natural log. Likewise, we can move on and look at the exponential function. So let's take a look at that. Here's another recall for a function we've seen before. The function is e to the x, although this will work for other bases too. I'll just illustrate it with e to the x. In this case, if you recall, the graph of e to the x looks something like this. It passes through 1 here on the y-axis and seems definitely, exponential growth after all, seems definitely to grow without bound. So, just to compare it here for a moment, I'll go ahead and draw in the y equals x line and then show you what the log function looks like in comparison to it. And you see the log function grows but seems to grow very slowly, whereas this one seems to grow much more rapidly and in fact does. So in this case, again without proof, we can take the limit of e to the x as x grows without bound to the right, that is toward positive infinity, and we seem to get infinity in that case. If we go in the other direction for e to the x, and in this case we actually can go all the way out because e to the x is defined for negative numbers, as x approaches negative infinity, in that case we can see that vertically, which is what the e to the x in every function that's under a limit represents, it is the vertical distance. This distance seems to be shrinking down to a height of 0. So the answer here would be 0, and I'm going to add something that's not usually added. I'm going to write from above, because we are approaching 0, which is the x-axis height. We're approaching that from above rather than from below or in some other manner. So it's nice to note that, even though there isn't any official notation for that. Also, just for the record, if we want to go ahead and look at the exponential with e to the minus x, then as you may recall, e to the minus x of course is 1 over e to the x, and that gives you a picture that looks like this, passing through 1 in the origin. And as you can see from this picture, if you take the limit of e to the minus x, as x goes far to the right, you're getting 0 from above, and the limit of e to the minus x, as x approaches negative infinity, goes far to the left, we end up with, you can see what's happening here, it's growing to infinity, infinity. So you see, if you have e to the minus x and compare it to e to the x, they are exactly reversed in their behaviors. Okay, there's one more kind of limit I wanted to talk about briefly here, and these are the trigonometric limits, which are the kind we'll be seeing in this course, although perhaps it would be better to say periodic functions. That's more general and in fact points out what makes these limits so interesting. These are limits as x goes to plus or minus infinity that do not exist, and they do not exist by reason of oscillation or something else. So there's no particular notation for this, but I can show you what's happening in a picture. So suppose first of all let's take the most familiar one, f of x equals sine x. If you look at the graph of this function, as we know, it never goes any higher than 1 and never goes any lower than minus 1, and has a picture that looks something like this in both directions. You can see that as x goes to plus infinity or negative infinity, the height of the function, the functional value, never settles down. It is what I like to call infinitely indecisive. It goes up and down and up and down. So if one were to ask the question, what is the limit of the sine of x as x approaches infinity, or for that matter as x goes to minus infinity, we would have to say it's undefined. And you can say it's undefined sometimes by writing oscillation. Oscillation just means that it moves up and down without settling down, but there is no particular notation here. If you remember, when we have functions that grow without bound in one direction or the other, we can put infinity or minus infinity, but there's no notation for this sort of non-definition. The other trig functions all are periodic in the same sense, and they can be even more dramatic. I won't write it, but with the tangent function, which actually breaks, say at pi over 2 and minus pi over 2, you will see that the function seems to go from minus infinity to infinity and then jump back down to minus infinity to infinity and oscillate in that sense with all of those gaps along the way. So it's even more dramatic. It's an even more dramatic kind of non-definition. But that's all that we want to say here, and we'll stop there.